So our first speaker, I'm very happy to introduce also old friends of mine and also well-known biostatistician, Ross Prentice. So Ross actually has many award, including he's actually a member of the National Academy of Medicine, and also he has received the COPS Award, and he actually also the former vice senior president and director of health director of public health division at the Fred Hutchinson Cancer Center. So he's well known actually for his important role in the Women's Health Initiative. And then so today, Ross will share with us about his thinking about intention to treat comparison in randomized trial. Ross?
So thank you, Andrew, for the invitation. Hi, everybody. I would like to have been there in person and was planning to it, but I re-injured a shoulder and had to stay close to home. So I'm going to go straight to sharing my screen. So this talk is likely somewhat atypical of the conference. I'm not even going to be using potential outcomes or counterfactuals. This really serves as a reminder of the causal interpretation that intention to treat analysis in randomized trials enjoy. So let's see. Trying to figure out how to get my slide to advance. Otherwise, we'll have to look at the same slide the whole time. That would be good. Somebody's trying to help me, but I couldn't hear you. There we go. All right. Thank you. So, can you hear me okay? Yes? Yep. Okay. So, I'll outline for my comments. I will be actually end up emphasizing the use of hazard ratio methods in randomized trial reporting. We'll use the Women's Health Initiative randomized controlled hormone therapy trials for illustration. And for motivation, I've listed comments from a couple of causal inference papers. Hernan in 2010 kind of cautioned the use of hazard ratios. He noted that an estimated hazard ratio has a built-in selection bias at times beyond randomization. Don't have a randomized comparison anymore if you fix that particular time. Then Odd Olin, Richard Cook, and Roisland wrote that the hazard ratio is not a quantity that admits a causal interpretation with unmodeled heterogeneity, which is true. But they went on to say that modeling frameworks more compatible with causal reasoning may be preferable for estimation in general. So I think when they wrote that, they had in mind estimands based on mean differences between counterfactual means. And so that struck me as going a little far because at least in the biomedical research area, as I recall, the counterfactual potential outcomes approach really came in as a way of trying to strengthen the reporting of observational studies through the emulation of clinical trials, through the emulation of intention to treat comparisons in clinical trials. So it seemed like a bit of a full circle to come back and say those frameworks are needed for causal interpretation in randomized, or preferable for causal interpretation in randomized trials. So I think the main point to make is that, say, the hazard ratio function is causally related to the treatment assignment in randomized controlled trials. So the randomization ensures a fair comparison between groups and what evolves, whether it's univariate or an entire function, like the hazard ratio function, is due to the difference between the intervention groups due to the treatment being applied. So there's lots of ways that one might summarize such a hazard ratio function. For example, an average hazard ratio estimation. Hazard ratio could be considered for summary, and that's what I will illustrate in hormone therapy trials. Actually, Hernan also commented correctly that the reporting using hazard ratios often uses an oversimplified model with a constant hazard ratio, making the interpretation unclear, and I'll come back to that at the end. So hazard ratio contrast in randomized controlled trials. We have a failure time variable subject to right censoring. Might have a covariate process that could involve some measurements at time of randomization as well as some subsequent ones. The hazard rate at times t greater than 0 is simply the instantaneous rate of failure at follow-up time t among individuals with a certain covariate history. In a randomized controlled trial, this covariate history might be very simple, just a constant for all times, where you might have z equals 0 in the control group and z equal 1 in the active treatment group. So intention to treat comparisons contrast hazard rates between randomized groups and therefore avoid confounding by pre-randomization factors. You need an independent censoring assumption, so-called, to ensure that hazard rates can be estimated correctly with censored data, in the presence of censored data. And intention to treat comparisons can be based on test statistics such as the log rank test, or based on various functions of hazard rates, including survival functions, which is the product integral of 1 minus hazard rates. So the causal interpretation for many other functional estimands, using Hernan and Robbins' What If book, said that causal effect can be defined as a contrast of functionals, including medians, variances, hazards, cumulative distribution function, etc. So one such functional to summarize, basically summarize hazard rates over the follow-up period, that has generated some interest, is the restricted mean survival time in the intervention group versus the comparison group. And that can be restricted mean survival time. Restriction means that conditioned on the failure occurring in 0t, can be written with a little integration by parts, just as the integral of the survivor function are written in terms of hazard rates this way. Another functional is the average hazard ratio, which can be defined as the ratio of the hazard in the intervention group to the control group, weighted by the probability distribution in the control group. You can symmetrize this if needed, if there isn't a clear control group. So P here is the failure time probability distribution in the control group conditioned on 0t, and you would only estimate this if for some T greater than T0 chosen to ensure some positive probability during the follow-up period in question. So this functional average hazard ratio is readily estimated non-parametrically by the expression shown here, where you have lambda hats, the Nelson-Allen non-parametric estimator of the cumulative hazard function, and F hats, the corresponding Kaplan-Meier estimator. And asymptotic properties for either of these, restricted mean survival time difference or average hazard ratio, derived from those for these non-parametric estimators, including bootstrap applicability. So now I will turn to two large clinical trials in the Women's Health Initiative. First was combination of estrogens and progestin used by about 6 million women in the US at the time these trials were initiated in 1993. And then among women who were post-hysterectomy, the same estrogen preparation without the progestin. The progestin was added to protect the uterus. So coronary heart disease was the designated primary outcome, invasive breast cancer, the primary safety outcome. There were about 8 years of follow-up to planned termination, followed by additional years of intervention. There are many other outcomes that are plausibly affected by these particular hormonal preparations. Some of them are listed here and are used in trial monitoring. And so both trials actually were stopped early based on, in the case of the combined hormone trial, higher rates of coronary heart disease, the primary outcome in the active treatment arm, as well as somewhat higher rates of breast cancer, invasive breast cancer in the intervention phase. And then after the stopping and the post-intervention phase, those somewhat higher elevations, especially for breast cancer, continued. In the estrogen alone trial, there were actually fairly similar rates of coronary heart disease and in the intervention and post-intervention phases. Whereas for breast cancer, contrast to the combined hormone therapy trial and not evident at all from extensive observational literature that preceded it, somewhat lower incidence with active hormone. And that continued in the post-intervention phase. So these are probably a little hard to see here, but just examples of the two non-parametric hazard ratio estimators on the left and restricted mean survival time difference on the right. And so you see for coronary heart disease and the combined hormones and early elevation and average hazard rate that drops off with follow-up. You don't really see much evidence of that with the restricted mean survival time, which is sort of insensitive to rare early occurrences. For breast cancer, there was a little bit of a reduction in this non-parametric average hazard ratio estimate at the beginning, very likely due to masking of the breast cancer diagnosis by the intervention itself, but that was overcome by increasing rates that were evident by about 7 years of follow-up. These were not so clear. They didn't become evident until maybe 13 years of follow-up for the restricted mean survival time difference. Corresponding plots for estrogen alone, not so much happening here for coronary heart disease with either non-parametric estimator. But for breast cancer, the average hazard ratio shows clear reduction after 4 years or so, and restricted mean survival time difference shows an increase after 8 or 9 years. So that's examples of kind of summary statistics based on causality related to the study design itself. Now, as the authors I mentioned point out, hazard ratio procedures, especially a constant hazard ratio, are very widely used in clinical trial reporting following Cox's seminal 1972 paper. So here the hazard rate function is modeled as a baseline rate and an exponential hazard ratio factor, where that hazard ratio variable in the XT can be defined in terms of the covariate history. Beta is a hazard ratio regression parameter to be estimated. And this is a really very flexible class of models that's useful and for many purposes in clinical trials. It's not just these intention to treat comparisons, but competing risk, multivariate outcome extensions are available now, and incorporation of post-randomization adherence and confounding factors. It's a great framework for that. And the asymptotic theory is well developed, including bootstrap applicability. Those estimators I just showed you in the hormone therapy trials look kind of noisy, and also they don't acknowledge the variable intervention time. Some participants joined as late as 1998 and others joined as early as 1993, so there's variability in their intervention exposure time that wasn't accounted for in those non-parametric comparisons. It might also be useful to acknowledge dependence of disease rates on participant age and other factors. So to apply the Cox models, you can stratify the baseline hazard rate without losing much in this kind of context in terms of statistical efficiency. So here are some of the other factors that were used in baseline hazard modeling. The modeled regression variable might allow the hazard ratio to differ in the intervention period. So for the ith individual, T0I is the length of time until the end of that woman's intervention period. Might also allow the hazard rate to be time dependent, just here in a linear fashion. After the end of the intervention period, you might have a different hazard ratio, and you might let that hazard ratio depend in a linear fashion on time from the end of the intervention period. So that's just an example of the kind of regression modeling that might be considered. And when you do that for these same analysis, the pictures look pretty much the same. They don't have a lot of that noise anymore. You see this elevation and early elevation in heart disease rates with combined hormones, and late clear increase in breast cancer with combined hormones with these average hazard ratio models. Similarly, for the estrogen alone trial, you see this clearer reduction now in breast cancer risk with longer follow-up, evident pretty early, not so early with the restricted mean survival time difference. So interpretation under Cox modeling, the overall hazard ratio from Cox models actually turns out to be virtually identical to a time varying hazard ratio with inverse weighted hazard ratios over a subdivision of the follow-up period. So in most applications, it's not going to be a serious limitation if you oversimplify the modeling. But if you use very simple models like a constant hazard ratio, you will miss some of the important information of the type just shown in the previous slides. To illustrate the first point, again, slide probably not that clear, but allowing the hazard ratio to vary over 1 year follow-up periods in the estrogen, the combined hormone and the estrogen alone trials. Top part is for coronary heart disease. And you can see if you make the simple proportional hazards assumption, what you get for hazard ratio and confidence interval versus doing an inverse variance weighted hazard ratio estimate using this subdivision of the time axis, identical, virtually identical for both trials. That's also true for the breast cancer outcome. Might be less true if you have highly varying follow-up periods for censoring. So interpretation of hazard ratio analysis, entire hazard ratio function, causally related to the intervention, various functions of hazard ratio, share that causal interpretation. So the hazard ratio at a particular follow-up time may well depend on hazard ratios at the earlier time, like Hernan was pointing out, but that's, I think, to be expected. So it's the interpretation of the hazard ratio function or summary measures from it is going to depend on how the hazard ratio evolves over time. Similarly, the hazard ratio function at a given follow-up time may depend on hazard ratio functions for other clinical outcomes that might be affected by the treatment, that is, competing risks. So if you're trying to formulate improved, if you like, reporting approaches for randomized clinical trials, you need to be dealing with other outcomes that may be affected by this. And I think the Cox model is really the most convenient and insightful way of doing that. And so if you have influence of a treatment on multiple outcomes, that may require a multivariate hazard rate regression analysis. And I have a couple of slides here, but I don't have a lot of time left, so I'm just going to mention them very briefly with the reference to a paper with colleague Chan Zhao and JASA in 2021. Say if you have a bivariate failure time, bivariate censoring, bivariate covariate history, you have marginal hazard rates, but you can also define a dual outcome hazard rate on the plane, the upper quadrant. So for example, the dual outcome hazard ratio at follow-up time T1 for the first variable and T2 for the other can be defined as a ratio of the dual outcome hazard rates weighted by the control group probability of failure up to that time, T1, T2. It's readily estimated non-parametrically and gives you some additional insights beyond treatment effects on the two failure time variables, effects on the dual outcome of related to that participants may experience both of those outcomes. And so I don't have really time to go into this, but if you looked at the dual outcome of breast cancer followed by death, there were 189 women in the combined hormone trial and the intervention group that experienced both of those outcomes compared to 145 in the control group. That gave a dual outcome hazard ratio of 1.26, bootstrap confidence interval away from the null. So you've got some new treatment information using these kind of hazard ratio methods. So to summarize, many hazard ratio contrasts have causal interpretation, including average hazard ratio, restricted mean survival time differences are examples, but you might want to choose one that fits your particular study context and population that you're studying. And these can build on non-parametric hazard rate functionals under the usual independent censoring assumption. Cox models provide a flexible and powerful framework for modeling those functionals and for many related quantities. And treatment effect assessment can be comprehensively carried out using hazard rates and hazard ratio for targeted outcome and competing risks. When I say comprehensively, that doesn't include topics like what the treatment comparison would be under full compliance, for example. That brings in additional analyses that have a different quality than these intention to treat analyses. And I think I just saw Andrew stand up, so I will stop at this point. Thank you very much.
Yeah, I stand up. I want to leave a few minutes for people to ask their questions, opportunity to ask you. Anyone from here?
While we get the microphone. Thank you. It was a great presentation. I really share the vision that the observation that the hazard ratios are maybe not that bad, but is it a little bit of throwing out the baby with the bathwater? Because what you are suggesting, as I understand it, is that you have to interpret the hazard ratio a bit more carefully and do more stuff with it. But really, why does our clinician friends love the hazard ratio? That is because it is exceedingly simple. So what is your challenge? How will you go about teaching the clinical environment these somewhat more complex handlings of the hazard ratio?
Okay, thank you. Good question. So the clinicians that I work with, who are large in number and come from various medical specialties, they actually warm up quite quickly to hazard ratio dependencies on time, follow-up time, and that helps with the interpretation. But I agree with you that the interpretation is complex. I think that's just part of the clinical trial comparison that's endemic. And that goes for any influences of competing risks as well. Those influence the overall interpretation of the treatment, as they should. And if you want to do other kinds of comparisons that are not based on the randomized comparison, that is not intention to treat, then you do need to make additional assumptions, and those assumptions are typically not wholly testable empirically. So there's a division, I think, in the analysis. It doesn't mean you stop with intention to treat analysis. You want to go on and do other types of analysis. Sometimes there may be evidence of post-randomization confounding, as we have seen in one of our other trials. And you might want to do some analysis that speculate on what the hazard ratio might look like if there was a different compliance profile, maybe fuller compliance. Those are all relevant questions, but they do entail a different set of stronger assumptions. And my reason for presentation here and the paper that it's based on was really just as a reminder of the value and simplicity of the simple intention to treat comparisons in randomized trials, and the value of hazard ratio modeling for elucidation of those comparisons. But I think I wouldn't underestimate the ability or the interest level of colleagues from other disciplines in warming up to complexities that may be involved in the problem and data summary. They're often better at that than we are as statisticians.
Thank you, Ross. Okay, due to time, actually, there are maybe other people who want to ask, but due to time, probably we'll move to the next speaker. Thanks, Ross, for the very exciting talk. Share your thought.